Okay, so we left off right here at our sine chart, and we were figuring out the different areas. And so one thing that you can do to help you visualize this function once you have your derivatives, once you know that on this section the derivative is positive, here it's negative, here it's positive again, we can see that the function is going to be going up and then down and then up again. So we can kind of visualize what that function looks like. All right, so our step number 4 is now we want to find the values. We want to find the y values and make a table at these critical points. So we found our critical points, and we know we're going to plug back in. We're going to substitute into our equation. You can use a calculator for this to find the y values when x equals -3 and when x equals 1, and we get these. In order to find out that it's a local max and an absolute min here, we have to graph it. So if we graph this function, let's see, what's the original function? X squared minus 3 equals e to the x. So let's pull up Desmos, and we can do x squared minus 3 times e to the x. So we see that this function has an asymptote right here at y equals 0, or y equals 0, and it goes down. Here's our absolute minimum. So that's why we call it an absolute minimum at 1, because this is the lowest that that function is ever going to go. And then we've got our local maximum right here at -3, because the function does get higher than -3, but in this open interval here, -3 is the maximum. And then, so then the last thing we want to do is write our analysis sentences. So sentences that we would say is f of x is increasing on -∞, -3, union 1 to infinity, because f prime of x is greater than 0 there. And we do include these points when we talk about f of x being increasing or decreasing, because these points are part of what makes it increasing. So it is increasing until we get to -3, and -3 makes it kind of an increasing function there. We say that f of x is decreasing on the interval -3 to 1 because the derivative f prime of x is less than 0 there. And we include -3 and 1 again because those points are helping, it decreases from -3 to get to the next point. So that makes it a decreasing function. We say there's a local max at the point -3, 0.299 because on the left side of that point, so x is less than -3, the derivative is greater than 0. And on the right side of the point, the derivative is less than 0. So it's creating that maximum. And then we can say that there is a local minimum at 1, -5.437, because f prime changes from negative to positive at x equals 1. And here we said local minimum instead of absolute minimum, which we set up here in the table, because using the first derivative test, we can only tell that it is a minimum. We can't tell if it's an absolute or a local minimum. We need to look at the whole function. We need to look at the whole graph for that. But here we can tell that it is a local minimum. Okay, next thing we're going to talk about is concavity. So we talked a little bit about that in class on Tuesday, but we've got concave down, right? And we've got concave up. So when we talk about concave down, we know that the y prime is decreasing. So now we're going to kind of define concave down. Instead of just looking like a hill, we know that the derivative is decreasing. If we look here and look at these tangent lines, here that the derivative is high positive, 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 0, negative, negative, steep, negative. So the derivative itself is decreasing, which means that the second derivative is less than 0. the derivative of the derivative is less than 0. For concave up, we can see that the tangent lines are increasing. They start steep negative, steep negative, steep negative, 0, positive, positive, steep positive. And so we know that the derivative is increasing, so y prime is increasing, and the second derivative is greater than 0. So this leads us to concavity. Okay, so our definition of concavity is for a differentiable function. It's concave up on an open interval. This is a key here, where for concavity we're only talking about open intervals. So it's concave up on an open interval if y prime is increasing. It's concave down on an open interval if y prime is decreasing. So we do have a test for concavity. And we can test the second derivative. So this is the second derivative test. It tells us that for a derivative that does have a second derivative, meaning it's twice differentiable, the function is concave up whenever the second derivative is greater than 0. The function is concave down whenever the second derivative is less than 0. And the last thing that we're going to talk about is what's called a point of inflection. A point of inflection is a spot where the graph has a tangent line. So that's important. It's where the graph does have a tangent line. We don't have points of inflection on corners like this. So it's where the graph has a tangent line, but the concavity and where the concavity changes. So here the graph is concave down, and then suddenly at this point right here, it changes to concave up. Here it's concave up, and it changes to concave down. So whenever it changes, that's called a point of inflection. So just real quick, think on what interval is this graph concave down? How would you write it? On what interval is this graph concave down? Hopefully you said on the interval negative infinity to 0. And remember, it's an open interval. We say that it's an open interval because points themselves don't have concavity. So we're not including that point in the concavity. And this leads us to our second derivative test. Alright, so we can test for local extrema using the second derivative also, as well as the first derivative. And the second derivative test says that if the first derivative is 0 and the second derivative is less than 0, is negative, then f has a local maximum. So here. So if our second derivative is negative, it means that we're concave down. So that tells us that we've got a maximum. If our first derivative is 0 and our second derivative is positive, that tells us the graph is concave up. So it's got a minimum. You can always think of it as concave down, like down is negative. A negative second derivative means it's concave down. Concave up, up means positive. So a positive second derivative means that it's concave up. All right. So let's do this problem. Find where the local extrema occur for this function and determine whether it is a max or a min. So try this one by yourself. See if you can do it on your paper. And first thing we want to do is find the derivative. So first derivative is here. We factor it. Okay. Second derivative is 6x. And now we want to find out where each of these are 0. So f prime of x equals 0 when x is positive 2 or negative 2. So that tells us at negative 2, let's see, the second derivative at negative 2 is negative 12. We plug in negative 2 here, we get negative 12. So therefore,